Okay, we're going to talk about the third case where we have complex eigenvalues. I've written out this example that when you use the same steps for case 1 and 2, you write out your equation so that you can see what A is, and you find the determinant in order to find your first and second eigenvalue, and we see that we have complex eigenvalues. Our first eigenvalue of 1 plus I, you do the work, same as before. You put it into your equation A minus lambda I times x equals 0, and we get this first eigenvector the same way as we find all of our other eigenvectors. I got the second eigenvector, though, just by saying that it's the conjugate, because that's what it works out to be. But you can do the work both ways to see if you get the same thing. You can pause the video and work it out if you like. Now, from these two eigenvectors, I've written out the solutions because we have our eigenvector and our eigenvalues, and I've written out the solutions the way we've known. So we write out the solutions the same way. The only thing I want to do is I want to distribute the 2 plus I1 vector to those two terms, and I'll do it down here too. And then after I've done that, I did skip writing that step out, but that's what you do. And then you take those two lines and you add x1 and x2, you add those two up, and then you take half, and this is what you get. Turns out that every time you add those two lines, you get multiples of 2, so we're able to take half. And then for our second solution, we subtract the 2, x2 minus x1, and then we divide it by 2 because they're all even, and then we also times it by I because you've got i's in there. Multiplying it by I will make I squares, and you get this second equation. So these are the two solutions we're going to use. Again, they're just multiples using the superposition of the original two that had complex in it, and these two solutions, which are linear independent, are also solutions. They form a basis. So now, what we've noticed is I write out my first eigenvalue, and I just want you to go here, first eigenvector. But the only difference is I write the second one, instead of 1, and I write it as a complex, because all reals are complex, so it's 1 plus 0i. So I write these out. I separate them from the real part from the imaginary part. And then notice this real part here, this 2, 1, appears in my solution 1. And this is a mistake here. This is 2, 1. And so that appears in my second solution also. The real part to my first eigenvector appears in my second equation. That's kind of crazy, but it does. It worked out that way. You're using a combination of both, and that's probably why. I did have to, when I was doing the algebra, I did have to factor out this negative in order to get this eigenvalue. And that was because I noticed that I had minus 1, 0, and that eigenvector would be eigenvector. I pulled out the negative there. And again, that imaginary part, this imaginary part, does indeed show up in my first and second equations. This is the real of my V1. This is the imaginary. This is the real times the sign, and this is the imaginary. So, again, the real part is the part without the I, and the imaginary is the part that's next to the I, and you write it without the I. So this example, in general, produces this form, as we can see. It uses both my solutions, use only my first eigenvector, and that's in general. I wrote that example in general, so we just extend this to all the cases of complex and to include alpha and beta. That example was 1, alpha was 1 and beta was 1. So we can just make an extension of that problem, and we can clearly put my alpha there instead of 1, it's alpha. And my beta, when you use the Euler formula, the beta comes to the equation. Comes to the angle of the sine and cosine. Okay? We can also take these two equations and condense them like so. And if you want to, this is the only, I would say you don't really want to condense it. If you want to memorize this, because this is easier, then you can use this to multiply out. That's my first equation. My second equation, it's this times this vector, and there's your second equation. So whichever one you want to memorize, these are the ones we usually use. Okay, so let's do our first example. We're going to do number 36 from the book. I'll write it out though. So here's our example. So what we're going to do is this. We're going to start off the same as the other cases. We need to find our eigenvalues, which I'm sure they're going to be complex because that's the example I want to show you. So we find the a minus lambda I, the determinant of it, which is 4 minus lambda, 6 minus lambda from the diagonals, 5 and negative 2. So all we're really interested in as we solve for the formula is I want to use lambda 1 in order to find my vector 1. So using a minus lambda I times x equals 0, we subtract that from my lambdas. So 4 minus 5 plus 3i, 5, we're just using this up here, minus 2, 6, but I'm subtracting the lambda. So we're going to set y equals to t. That's the one I prefer. And I'm going to plug it into this second line, minus 2x plus 1 minus 3i times y, but instead of y, I'll write t, and this way I can solve for x in terms of t. So xy is equal to y was t. So we can multiply top and bottom by 2, each of those, and get 1 minus 3i, 2, t. What I have next is v1 is 1 minus 3i, 2, and we can break this up into 1, 2, and minus 3, 0i, because it does not have a complex part, an imaginary part. That's 2 plus 0i. So what we notice, though, is be very careful. We can't divide out by a 3 top and bottom here, because this is a part of this. If we want a 1 there, you'd have to multiply top and bottom by 1/3, and you'd create 1/3 here and 2/3 there. So we don't want that. This is the least amount of fractions. So we're not allowed to reduce the real part and the imaginary part. You can only reduce them together. Going on, now we're able to use our formula. So x1 is E. And what's my alpha and beta? I have to go back to the eigenvalue. Lambda 1 equals 5 plus 3i. So my alpha is 5, and my beta is 3. The real vector 1 is 1, 2. These are just my two solutions. If I want to write it in general form, x equals c1 x1 plus c2 x2, I have my x1 x2, but that's quite long. There's a way we can shorten it a little by writing out x1. What we're gonna do, use a height, I'm gonna write out my two equations. Okay, that's my first equation. We write it basically as a matrix. E to the 5t is 1 cosine of 3t plus minus 3 sine of 3t. The bottom is, I use the bottom one. And we can see one of the terms zeroes out, so my bottom is just, oops, I lost a 3 there, 2 cosine of 3t. So writing out our second solution, I can see the top, minus 3 plus 1. So it's minus 3 cosine of 3t plus 1 sine of 3t, which I don't need that one. The bottom, the first term zeroes out, I get, that's a plus, sorry about that, I lost that. And the bottom, I get 2 sine of 3t. And now for my general solution, x is equal to c1 times my x1 plus my c2 times, I'll cut and paste my second, and there we have it. That's my solution, my general solution.